Alright. Did you guys remember what we discussed last time? This whole course is about relative motion. Do you remember what specifically we discussed? We discussed relative motion. What about relative motion? So last time we arrived at the two-body problem statement, right? The two-body problem statement says R double dot plus mu over R cube R is equal to 3. Right? And then we said if we throughout this course our focus or our intent big goal is to find R. Okay? And this is position of orbiting body. With respect to central. Okay? And we said if you want to find R from this, you have to integrate this equation twice. That means we'll end up with two constants. Right? So if you integrate once, you'll end up with one constant. Right? You remember that. You integrate it again. The back door is 4. You integrate it again, you'll get another constant. Now, since this is a vector, we're dealing with vectors, there will be 3 plus 3, 6. We need 6 constants. Okay? We started with saying we can define 10 constants. These are called 10 constants of two-body system, okay? Or two-body relative motion. And the last class we discussed, we said angular momentum is conserved. If you write it mathematically, you say H is equal to R cross with R dot, right? So do you understand why this is 3 constants? This is a vector, right? H is a vector. So it's 3. If it's constant, it has to be 3 constants. Okay? You'll understand what this means, but just to give you a start, see, whenever you calculate this quantity at any position in the orbit, if you calculate r cross p for a given two-body system, it's going to be constant. R will change, r dot will change, but the cross of this will always remain the same. That's what this means. Okay, so what it means, another way, if you know one of them, you should always be able to figure out the other. If you know this for one orbit, for any given orbit, or for any given two-body system, you can always assume it's going to be constant regardless of where the body is. And knowing one, you can always derive the other. That is what it means. Okay? Today we're going to discuss the other constants. Let's start with total mechanical energy. How many kinds of forces are there? Any of you have a physics background? You should know, but you are minoring in physics, double majoring in physics. How many kind of forces are there? Gravitational force. So you have to really get this drilled in your head. Forces are only four kinds. Okay. You said gravitational, right?
I'll agree with that. That ain't right.
Yeah. Gravitational, electromagnetic, strong and weak nuclear force.
The CERN would disagree, the scientists at CERN would disagree and say that gravity is not a force.
Yes, we are leading there, but you should, until now, as we understand it, it's not true. Gravity is a force. Weak nuclear force and strong nuclear force. So what is weak nuclear force?
The force that keeps the nucleus together.
That is the strong nuclear force, right? So if you have protons, protons are what? Positively charged particles, right?
Yeah.
Now, there has to be some force to keep them together. Why should there be some force?
What a force for what nucleus bubbles?
Yeah. What is the nucleus made of?
Neutrons and protons.
Neutrons and protons. Why do you need a force?
Oh, because neutrons have no charge. So there's no reason for them to be there. What? No, neutrons have neutral charge.
Neutrons have no charge, but protons are
Positively charged.
But do you see that all the neutrons are just
They should repel each other. Right?
they should go apart, right? If you have a positive. So there is some force which is binding them together. So that is the
Strong.
yeah. So you have, when you're talking about total mechanical energy, what are the two types of energies you know of? Huh? Mechanical energy. You have kinetic energy, right? And potential energy. Okay. So what it says is total mechanical energy. When you add this of any system, this total mechanical energy is always conserved. Okay? That is what we want to prove. Is energy a scalar or a vector?
Scalar.
It's a scalar. Right. So again we start with the two-body problem statement. Keep in mind, this is something we are going to expect this in an exam. Okay. Given the two body problem, arise, show that angular momentum is conserved, or show that the energy, total mechanical energy is conserved. So we start with this. We use total mechanical energy. Use epsilon, okay? So epsilon to denote total mechanical energy. We call full body problem. R double dot plus over R2. How do you express kinetic energy? Do you remember? Huh? 1/2 mv squared. How do you represent potential energy? Essentially GH as a potential height. So that's what we are talking about. So you have R dotted with R plus mu over R2 R dotted with R or 0 not a R dotted with R is what? A vector dotted with itself? No.
One is the vector square.
Vector, the scalar square. A dotted with A is equal to
AI.
So it will be A cosine of AA. Okay. This the angle between the same vector is 0. Angle between the vectors. This is 1. Okay. So this will be cosine of angle between the two vectors. The two vectors are A and A. Right? It's the same vector. So you have A square. So you get R square over here. You have R dotted with plus mu over R equal to 0.
Why can't you just take the R out of it? Why can't you just take all of the R's out of it? There's an R in every term.
R?
Yeah. You got R double dot divided with R, and then in the second term you got two R's, and then on the other side of the equation you got R. Can't you just take all the R's out?
No, I want to do that. I want to dot with R. So if I take it back, then the whole purpose of dotting it with
Extra.
going back. say, let's call this equation A. Sammy, can you move it a little bit?
So DJ intervention.
Keep moving, keep moving. Yeah, that's it, that's it. Is it visible to you guys? Zoom? To analyze equation A, there are two terms, okay? First, let's do mu over r d over dt of r. So I'm going to say, I can write this one, or let's call this r dot with r dot with r. So what is this? You have 1 over 2. R dot order with R double dot plus R dot order with R double. Right? So this is R into 2 R dot order with R double. Right? This is equal to this. Correct? Any doubts?
Well, you get that. Chain rules kind of awesome. But it works because they're all the same frequency.
It's actually not right.
Yeah.
Why so?
Because it should be.
Right. You're missing a dot over here. You're actually dotting with R dot. we need to dot this with r dot. Okay. So this is r dot. This will not change. Green arrow. Now it makes sense, right? I have not done anything. See, I tried to dot it with R. I couldn't get it. So I dotted with, I'm dotting with R dot. Everything else is very systematic. It's not changing. You see that? Dot, dot. So I'm analyzing this term. Okay. This term, I'm telling this term can be written as this. So what we did was d by dt half r dot with r double dot plus r dot dot with r double. Right? And this is okay. What do you see here? What is this? Or what is this? Huh? It's right. It is half r dot square, right? Half d square. Okay. Half d square. Say it again. Specific kinetic energy. This term is specific kinetic energy. So what we also see here? What is this? This term? Specific angular moment. Okay. So we are dealing with specific quantity. Specific just means per unit mass. Okay. This is one. Now, so we have proved that this can be written as d over dt. Okay. Now let's analyze the second part. What is the second part? We have mu over r cube r dotted with. Now one of your again aside this will be part of your homework. A vector dotted with its derivative equal to scalar into its derivative of scalar. So you have to prove it as part of your homework. Okay. lead you to this. So we're going to use this relationship here. The vector dotted with it, this can be written as mu over r cube r dotted with r. Okay? Sorry, not r, just scale. Okay? We have one square. Mu over r square. Now I'm going to say this can be written as d over dt of mu over r. Maybe. If you look at this, if I split this open, what would this be? If I split this open, what is the derivative of minus mu over r? Hmm?
What, you trying to separate the two? You said split it open. Well, mu is constant.
Mu is constant. So
negative mu over r dot.
you guys have forgotten everything. You can't take the derivative of 1 over something. What is the derivative of something over?
He's right, it's 1 over r squared.
Yeah. Minus mu over r squared. Okay. And since this is a function of time, you only get r dot. Okay. You take the derivative. Derivative of see, we have d over dy of 1 over y, and y is an implicit function. So if you want to do that, you're going to get minus 1 over y squared, right? Into dy over dx, or yeah. If you have y as a function of x, okay, take the derivative with respect to x, you're going to get minus 1 over y squared into dy over dx. We call it the function. Okay. This is a complete derivative.
Right, so with that principle in mind.
Yeah, so this would be plus, right? And these two are equal, correct? If you combine B and C into over dt of r square, r dot square minus d over dt. Or d square over 2 minus mu over r equal to again, what I'm using this, that if the derivative of something is 0, it is that something is a constant, and the constant is denoted by capital epsilon. So what we have proved here is, this is your specific kinetic energy component, this is your potential energy component. Okay? And this equation is called Vis-viva equation. Okay? Vis-viva equation of energy equation. And it says total mechanical energy is conserved. Any doubts until now?
Why did you where seated? Where seated?
C?
Yeah. Why did you write negative u over r and take the derivative?
See, I'm saying this can be expressed as this. You look at this one. I'm saying this can be expressed as this. D over dt. Okay. And what we saw here is, if you just take the derivative of this, you will end up with the same term. Now, if you're talking about, we'll just end the discussion with conservation of linear momentum. Okay. How do you express linear momentum? mv. If mv is constant, or if mv is equal to 0, what do you need? Sorry, mv is equal to constant. How do you prove mv is equal to constant?
You have to set a to 0. Yeah, so second derivative would be
Acceleration should be 0. Have we proved that acceleration is 0?
Yeah.
When did we prove that?
No. When we said that this is an inertial frame.
Right. Inertial point. Right.
Yeah.
So when we proved the inertial point, we proved that acceleration of that system is 0. And mass is definitely 0. Right? So velocity is mv is constant. So we've already proved that the linear momentum is conserved. Okay. See, because linear momentum is conserved, the gravitational forces, you can think about what is the original form of Newton's law? Newton's second law.
Observation of momentum. So it's integral of mv.
The applied force
Force is equal to time rate change in momentum.
right. Applied force is equal to time rate of change of linear momentum. Right? If this is constant, this is 0. Right? And we have proved this to be for a two-body system. Linear momentum is constant, which means there is no external force acting on it, and that is what we operate under, right? The only external force is gravitational force, and we assume that the gravitational force is it's constant, right? So to wrap up, we'll take a look at the solution to the two-body problem in next class. But for your exam, what you need to know is there are 3 derivations we have done until now. One is starting with the Newton's law of universal gravitation. We arrived at the two-body problem statement. This is a two-body problem statement. We started with Newton's law of universal gravitation. We used two laws, Newton's law of universal gravitation and which was the other one? You remember? Use the second law, Newton's second law. F is equal to ma, or F is equal to change in linear momentum. Okay, so you should be able to use those 2 laws for a two-body system and arrive at this. You have to practice it over and over again. The second derivative we looked at was this one. Okay. See, what this means is over the period of time, over the duration of this course, you'll understand that orbits are limited to Keplerian orbits are limited to a single plane. You know what that means? See, the plane in which Earth is rotating around the Sun, it never changes. The plane always remains the same. So that is a consequence of conservation of conservation of angular momentum. Because the angular momentum is conserved, the plane remains the same. In the sense, if you have a two-body problem, if you have this central body, you have an orbit, right? Where is your, how do you take a look at this in a little more detail, but what is your R here? This is your R, orbiting body, central body. Okay, this is your R, and this would be your V. Okay. If you cross those two, what direction would the cross product of that vector be? Huh? What direction the cross product of any two vectors? Perpendicular to the two vectors. You take two vectors, any two vectors, and cross them. The cross product is always perpendicular to both vectors. Okay? So you take any two vectors are going to always form a plane. Correct? You take any two vectors, they are going to form a plane. And you cross it, that vector is always perpendicular to that plane. So this R cross V, H vector is in what direction? In here. If the rotation is in this direction, H will be here. It will be coming out of the board. Right? R cross with V. Right? You have R, you have V. You see this? You have R, you have V. H has to come this way. has to come in this, has to come outside of the board. This h is conserved, h is constant, which means it does not change its direction or its magnitude. So that plane has to be the same, because if this changes, that plane changes. Okay. So this is the other derivative you need to practice for exam. Starting with the question will be starting with the two-body problem. I will not give the statement. I may not give the statement of the two-body problem. Arrive at the conservation of angular momentum statement, or show that the motion is related to a plane. This is the second derivative. The third one is total kinetic energy. Okay. These three are what we have done until now. Alright? So